We've seen this, you've watched this movie before, it's got some narrative to it. We use this to talk about jet blast, blow you away, I guess, the truck that was being blown off the runway at San Francisco International Airport. And so what we never did mention when we're dealing with that was the fact that when we looked at the velocities that would come from this jet engine, we never looked at a streamline, for instance, that would actually go through the jet engine. So when you're upstream on the front side of the engine and you're downstream on the back side of the engine, with going through the actual workings of it, then that deals with a condition where our system is not closed to energy inputs. And so lots of energy systems that we'd like to deal with have energy inputs into them, such as pumping fluids from a low location to a high location, as in out of a well, or in terms of the opposite, in using flows from a relatively high location to a low location to actually generate power. And so a couple of examples of why we might want to look at what we're going to look at would be things like pump storage schemes. And so pump storage schemes really just rely on the fact, I guess it's not, is it going to get any larger for me? Maybe I can do this. Is that one of the issues, not with fossil fuels, which are great baseload fuels, you can turn especially for natural gas, you can turn gas turbines on, which are actually basically the same turbines you saw sitting on a 747 there. And when peak demand comes, you just ramp them up and they ramp up instantly. Not so much for coal, which is a bit slower to ramp up. Not so much for nuclear power, which is slower to ramp up as well. But one of the big issues with renewables is its intermittency. So you only generate electricity from wind turbines when the wind blows, and you only generate electricity from PV cells, photovoltaic cells, when the sun shines. And so that has to be used instantly. And there's no easy way to store energy, electrical energy, on the grid. You can't make big batteries to do it. And so you have to resort to physical means. And so physical means to do this are two that we can look at here. One is pump storage schemes. That is that you have a lower reservoir and an upper reservoir. When you need power, you drain the upper reservoir through a generator or a turbine to lower power and generate power to be able to add to the base load for peaking when everyone turns their toasters on in New York City at 7 o'clock in the morning, or kettles, whatever it is. And at nighttime, when no one needs power anyway, then you do the opposite. You take water which is stored in this lower reservoir and you use low-cost electricity that you have in the grid, which is in surplus because it's being supplied by base load, and you supply it to an upper reservoir where it has potential and then can run back through the system in times of peak needs. And so pump storage schemes are reality. I was surprised that actually in Pennsylvania there are a couple. I'm not sure whether this is, I don't know anything about this. This is on the Susquehanna. The one that I know of is in Kinzua Park. So northern Pennsylvania, near Kane, Pennsylvania, I guess up in the plateau area. And this is exactly it. It's a river with a dam impounded behind the river. The river generates power through it. It's probably the Allegheny River. Yeah, it is the Allegheny Reservoir and Allegheny River. So it generates power by running fluid through a conventional dam. But in times of low demand, it's pumped up to this upper area where it acts as a big battery that can flow through the system after the fact. The other way to deal with this is to use what's often referred to as compressed air energy storage. And so this is basically the idea to use potential energy in a different way. So instead of elevating fluid to some location in times of low electricity demand and surplus electricity, you use it to compress air, and you need somewhere to do it. You could do it in a tank, but it's much more easy to do it in underground caverns. These caverns are often the same kinds of caverns that you use for the Strategic Petroleum Reserve, which is, I don't know how many billion gallons of oil in Louisiana salt domes, where these caverns have just been eked out by drilling a hole down, circulating warm fluid, warm water in the hole to be able to dissolve the salt out of it, and then retracting the casing up so that you dissolve this plug that ends up looking like a big vertical cigar, and that is an open cavern which has just been dissolved out by solution. You pump air into the system when you have underused electricity in times of oversupply, and you run it back through compressors when you have it when you need it to top up baseload. You can do it merely just with the pressure that you apply within this cavern to do that, or you can also do it by, for instance, displacing water up to the surface, almost like this pump storage scheme. You pump air in, it displaces water, water goes up to the surface. When you need to recover the compressed air underground, you allow that water to go in and force the air out, and you're basically recovering the energy from the change in elevation of a dense fluid as it goes down maybe a couple of 1,000 feet, 1,000 meters into the subsurface. And so those are ways that can be used to be able to make up for the kind of the vagaries of the intermittency, if you like, of power systems, renewable power systems. And so what we want to deal with now is to be able to apply the same principles that we've applied for both conservation of mass and conservation of linear momentum to be able to deal with this. And so in each of these, we've used this expression for Reynolds transport theorem. We know that in this transport theorem that this is really, at least for conservation momentum, its sum of forces is equal to mass times acceleration. This portion here has been the part that dealt with this. And we localized behaviors in terms of this quantity lowercase b, which was uppercase B per unit mass. And for the two systems we dealt with, B was equal to, uppercase B was equal to mass, which was equal to density times volume. This V here is velocity. Area times length would be a volume. But for conservation of mass, the parameter that we dealt with was mass. Mass per unit mass is equal to 1. So the value for B is equal to 1 when we deal with it for conservation of mass. And for conservation of momentum, it's just equal to mass times velocity in this particular case, which is the same as being equal to density times volume times velocity. This is V for velocity. We will score through our V's that we use for volume, just as a standard procedure. So these are the two that we've looked at so far. So in week number 6, this is what we dealt with. Week number 7, we dealt with this. And now week number 8, the quantity that we'd like to deal with is going to be equal to mass energy per unit volume. So the intrinsic quantity we'll use is going to be equal to energy per unit volume, per unit mass, sorry. And this is equal to the internal energy per unit mass plus a kinetic term, V squared over 2, plus potential energy. And so in our particular case, we'd use uppercase B as the total quantity. The quantity per unit mass is that total quantity divided by mass. And in that particular case, when we look at basically kinetic energy in our particular case, this is internal energy. So this is This is kinetic energy. And this is potential energy. So the same kinds of things that we talked about in pump reservoir streams. And so what we can do is, with this energy per unit mass, we end up being able to also define an extra term that includes this internal energy per unit mass and also the magnitudes of pressure. So we can also define the term for enthalpy. And I don't know what terminology you use in Lubish's class or Jeffrey's class, but the book uses H, and it's equal to two components. It's equal to the internal energy per unit mass plus the pressure divided by density. And so what this allows us to do is to take systems like, for instance, the jet engine, where you have a change, an enthalpy input into the system as a result of going from upstream of the engine to downstream of the engine. You're putting chemical energy into the system. And it allows us to take care of the case where we're adding energy into the system, which we haven't done in Bernoulli. A consequence of Bernoulli, which is also, this is really just a restatement of Bernoulli in much more useful coordinate systems. Conservation of momentum is just Bernoulli, as it turns out, is that there can be no net energy into the system, and there can be no net energy losses in the system, because we deal with one of the consequences of Bernoulli is that it has to be inviscid. There is no energy loss within the system. So now what we can do is we can deal with terms that actually look a bit like Bernoulli, that have the kinetic energy term, V squared over 2g, the potential term, Z, and also the pressure term, P over rho g, if you remember this, are the three terms which are in Bernoulli, but also allow us to be able to input energy into the system in terms of this internal energy as an input, or losses within the system, which would be the negative of that. And so that's what we're attempting to do now. And so really what we're doing is being able to deal with that in some reasonable way. The easiest way for us to think about this is that if we deal with it first in terms of this idea of Bernoulli as a pipe, which in this case might have a jet engine put in it, or a pump. So if we think of this as a pump within our system, then one way that we can think about this is that if we take a datum that Z is equal to 0, and the easiest way to think about it, all the stuff that we'll do in terms of energy conservation in this part, week 8, will all be not using Reynolds transport theorem as defined here, but using it in just a one-dimensional form, and so along a streamline. And so the easiest way for us to think about it is in this one-dimensional form, where it's a streamline. That streamline goes from a location that is upstream to downstream, and we can define it in terms of an elevation as it goes from upstream to downstream, a pressure that we might have, P1 and P2 downstreams. I suppose we'd expect these to be the same, right? If it was actually a constant section pipe. Oh, that's not beer. And we've called this the hydraulic grade line. And, well, actually we wouldn't expect it necessarily to have the same pressures, but on top of this we might expect the velocities to be the same if it's constant section, just from continuity. And we call this the energy grade line. And that's how we've thought of things. But what we could do is we could think of what we might call as the energy grade line on steroids, or a secondary one. that goes across the top here, which is horizontal. And that has, well, I didn't put this on. This is V1 squared over 2G. And this is V2 squared over 2G. But to have another component which allows us to have two things. One is that it allows us to put in an extra amount of energy, which we'll call pump head. I guess I could write it out. Equals pump head. And to also allow us to put in something which is head losses. And so what we could say that is within our system that we want to take this upper energy grade line, this dashed line across here, and that defines our system. So in the same way that we wrote Bernoulli between an upstream, so I guess I should make the case that this is thinking about something. This is velocity 2. This is velocity 1. They are streamlined velocities, right? So you could think about them coming across kind of a control volume at the end, but it doesn't really matter. We can just write them in the same way as we wrote them for Bernoulli. But this is upstream, and this is downstream. Very important. We made the point before that we don't have to do that if there's no losses in the system. You can write it upstream or downstream, backwards, forwards, it doesn't matter. But if we want to write it in terms of energy, because energy is lost and dissipated from the system, so the analogy I always use is dragging this bag across a table. That to take it from A to B, I have to put energy into it, and then it rests there. To get it back to A, I have to put more energy into it to put it backwards. And so it takes energy both moving it in one way and putting it back the other way, and so it takes double the amount of energy to get it back than it did to move it one part. And so it matters that we're dissipating energy. And so if you imagine that we now write these components out in terms of Bernoulli, then you can imagine that if we write this in terms of the upstream, then we have an equation like this. This is just Bernoulli written as before. So it's written unconventionally. Actually, why don't I write it properly, the way that we've written it. So upstream has been P1 over gamma plus Z1 plus V1 squared over 2G. Those are the parts that we're familiar with. Plus the amount of energy we put into the system due to pump head, which is HP. And that has to equal the stuff on the downstream side. The pressure downstream, the elevation downstream, the velocity head downstream, and the head loss that we engender by going downstream. And so this is really just this equation here written out in a slightly different way. You'll notice that it's written backwards. This right-hand side is really, this is the upstream. This is the downstream. But it's exactly the same expression as this. And the only things that we've added to it are two terms. One is that we have a pump head that is added into the system. So you can imagine that between the upstream and the downstream, we're putting some energy into it in terms of pushing the stuff downstream, which allows it to have more energy in the upstream. And so in terms of convention, I guess you can see two things from this. All of these terms are individual lengths. So this has to be a length, a head. And so this is, in our terminology, positive if a pump. It's negative if it's a turbine, just by convention, if you write it upstream and downstream. And head losses, from the same analog as pulling my bag across the table, you always use up energy within a system, whether you're flowing upstream or whatever direction you're flowing, and so this is always positive, and everything else remains the same. You'll see in here that there's an extra expression here, alpha. We could think about adding to each of these terms, and alpha merely refers to the fact that if you have flow within a pipe, we assume, using Bernoulli, that the velocity distribution of that flow, if for instance we looked at a portion of this pipe here, then this flow, if it's uniform, then alpha is equal to 1. If the flow happens to be non-uniform, such as this, then alpha is less than 1, or it's at least not equal to 1. And so it's just a multiplier based on what we think the flow is. And so I'm not sure we'll use that very much, but it's typically a term that's added in this. And it could be different upstream and downstream for if we know what the distribution is. So that's the simplest exposition, if you like, of the energy equation. And as we say, the terms really are Bernoulli-esque, upstream and downstream. They mean the same thing as they did before. If you recall, this is equal to F equals ma on either side. Sorry, wrong way around. Don't write that down. F equals ma. This v squared over 2g term is just the acceleration term, and that applies on both sides, and that's really physically where it comes from. So the energy equation is no different than solving for conservation of momentum. In fact, I guess you could think about it is that if you look at mass times velocity, and if, for instance, you integrated that with respect to velocity, you'd end up with this. And so this is what we know is momentum, and we're interested in rates of changes of momentum, and the quantity of kinetic energy, half mv squared, as we know, is really no different from rates of changes of momentum. That's physically what it physically means. And so we're not doing anything with changes in this behavior other than saying that we can write Bernoulli again to be able to deal with the problems that we want to, but now we don't have to limit ourselves to an inviscid force or an inviscid fluid, but the fluid we use can be viscous. And we accommodate the viscosity in a loss term that by flowing fluid along a pipe, there's friction along the pipe, and therefore you're dissipating energy by generating heat, basically, in the system. And that we can also put energy into the system, such as by chemical reactions inside this jet engine, to be able to take a flow velocity ahead of the jet engine to a flow velocity downstream of the jet engine, to be able to calculate things like how much thrust you might have. So that's what we're attempting to do with energy. So that's the easiest way to think about it. And this is, if you like, the physical description of what's going on. So if you like, this is the physical. We haven't said anything about the chemical way of thinking about it. And when we look at internal energy within a system, we really are trying to lay out the groundwork for being able to look at the chemical response. And so the other way for us to look at it is that if we take Reynolds transport theorem and do some things with it, we can end up with this expression, which is exactly Bernoulli, but with a loss term and a pump term that allow us to be able to deal with energy in the system. The other thing that we might want to be able to do is be able to do things with enthalpy when we look at chemical potentials within a system. And if we do that, it gets kind of nasty, but the basic idea is that if we look at conserving mass, we can write this expression here, Q net in plus W net in is equal to sum of mass flow rates multiplied by internal energy plus pressure over density. And so this is a thermodynamic statement, if you like. And I guess the other statement that we had is something that looks like sum of forces is equal to mass times acceleration. Another way of writing Newton's law is the rate of change of velocity is acceleration, but you can think of it as a rate of mass flow rate in the same way. So this expression here is our conservation law, if you like, from linear momentum, what it works out to be, right? This is mass flow rate, and this is a velocity. So there's a mass flow rate is a density times a velocity times an area, this term here, multiplied by a velocity. So this is conservation of linear momentum is equal to the sum of the forces. So that's what you dealt with last week. The equivalent to that for the energy equation is this. This is a mass flow rate. The multiplier on this, instead of just being velocity, is the internal energy and the fluid pressures. And since we know that we can write enthalpy in terms of this internal, this is the total energy per unit mass. The internal energy is this term U. The fluid pressure term, which goes here, when you add this in, it means that you have both U and P in the same expression, and you can rewrite this as being equal to the sum of the mass flow rate multiplied by V squared over 2 plus GZ plus the enthalpy. And this is equal to Q net in plus W net in, which we haven't defined yet. So the bottom line is, in the same way that when we conserve for linear momentum, what we can do is we can conserve for internal energy per unit mass that includes these two terms. A fluid pressure term, don't worry about where it comes from. When you substitute the terms for internal energy into this, you end up with enthalpy, velocity squared, Gz, and pressure. We can combine the internal energy and the pressure together in enthalpy, and we end up with this other expression here, which is written. And so we can talk about the individual terms. The sum of flow rates is this term here, just written as lowercase m. There's a reason for that, but we'll talk about it later. The other term is the enthalpy, which is this term here. The other term is V squared over 2G term, which is this. And the other term is potential, which is just the elevation. And so this is like Bernoulli. This is Bernoulli velocity squared term, the elevation or potential energy term, and the pressure is included in this component here, but it also has a chemical part included relative to it as well, this internal energy, which allows us to be able to put energy into the system. And so what we can do is we can equate this power, I guess, rate of doing work, with two components. The amount of heat energy that goes into the system, the rate of heat energy, the dot is how quickly it goes in, heat energy per second that goes in the system in terms of thermal power, and also the work, rate of doing work. So this is mechanical power, and this is thermal power. And the sign convention is what we have to deal with, is that the sign convention is that positive is if you're putting energy in, hence it says net in. I know it's getting a bit crowded. Positive work is also when we're putting work into the system. And mass flow rates are always positive. Doesn't matter whether it's going in or out of the system, as we used it when we talked about conservation of mass and conservation of momentum. This equation is just a one-dimensional equation, again written along a streamline. And so mass rate is always positive. Number is always positive. And velocities are always streamline velocities, so they're always positive. And elevations are positive vertically upwards. And enthalpy is positive in increasing enthalpy. So that's the sign convention we have to do. And so really it's a similar exposition to the one that we did for Bernoulli's equation, which is this, just with these components, but it's written in a way that now includes the chemical energy that can be put into a system. So it's useful in that way. They're equivalent to each other, they're just written in slightly different ways. And we'll use them in different ways depending on what our end result is. Yeah, sorry.
Why is it not negative for the HL in the very bottom equation?
HL is because it's added onto the right-hand side. So it's, yeah, because it's already gone through the system, and in going from a higher, you could think about this as being a slope down here as it goes to here. It's lost this amount of energy as it goes from upstream to downstream. Yes? Can you shout, please?
How come work into the system is positive?
Just by sign convention. It's just, yeah. I mean, it's the same. We haven't derived it, and so I guess we could have derived it. I don't want to derive it because it's these 5 or 6 or 7 pages. But you just need to take it as a convention that's the sign convention that works. Maybe not a very satisfying answer, but it might be a practical one. Okay. I mean, it could be either way, right? It has to be either positive into the system or negative out of the system, and it would have a negative sign or a positive sign attached to it. So with the way that this is written I guess you could write it the other way around. You could write it as negative if you exchange these around for each other. That's all. So it's just a sign convention. But they are scalars. These are not vectoral quantities. It's a scalar magnitude. It's written this way. The units of this have to be in terms of power. So joules per second, Newton meters per second. And so everything else in this should be consistent in terms of those, and you could check the magnitudes. The other thing that is useful in these, maybe, is in being able to, since these are both consistent with each other and just have different uses, then there should be some consistency in being able to convert head losses and power inputs into the system in terms of work. If you put power into the system in terms of a pump, you're putting work into the system in that particular case. And so you can relate the magnitudes of the pump head as a function of the work into the system divided by gravitational acceleration. Or if you want to substitute this in here, then you can also write the pump head, getting very crowded, I apologize for that, as being equal to W shaft in divided by G times the mass flow rate. And so this has to be in units. Well, you can work out whether the units of this make sense or not, but the left-hand side of this has to be in units of length, and the right-hand side has to also be in units of length. I guess we could do that, right? So let me choose a different color just to show whether that's the case. So work rate is power. So power is joules per second. Gravity is in meters per second squared. And mass flow rate is in kilograms per second. So get rid of seconds. A joule is a Newton meter. And a Newton is a kilogram meter per second squared. And so if I use a red pen, maybe you can see if we start crossing things out, we should be left with units of length. So we get rid of seconds squared, we get rid of kilograms, we get rid of meters, and indeed we're left with 1 meter in the system. And so if you take something out of today, we've jumped around a little bit, but take a few things. One is that there's Bernoulli's equation that has these extra terms in it to allow us to put energy into the system, is pump power, and to have head losses in the system, which allow us to deal with fluids which aren't inviscid but actually have viscosity in them, such as typically is the case in pipes. The whole idea of being able to calculate flow in pipes and well bores and porous media, for that matter, are the losses that result from viscous losses. So this term is an important one that isn't accommodated just by Bernoulli's equation. Remember the sign conventions, that this is positive if you're putting energy into the system as a pump, negative if you're taking it out as a turbine. These are always positive. You always have to write it from upstream to downstream. So depending on how you look at the 1s and the 2s, these two equations are exactly the same as them. And we probably won't use these alpha values. They're just scalar values which are non-dimensional, which are just 1 or a number smaller than 1, depending on whether we deal with it. So that's Bernoulli's equation with these extra terms added. If we want to not just look at physical systems, but look at chemical systems, such as a jet engine, for instance, where we're putting chemical energy into the system, then we can include the idea of enthalpy into the system, and we end up with exactly the same Bernoulli equation, with the velocity squared term, the z term, and the pressure term embedded within the chemical energy system, which is this, pressure and internal energy per unit mass. And we also have to remember the sign convention for that. If we're putting heat into the system, it's positive. If we're putting work into the system, it's positive. The mass flow rate is always positive. And we have to write it between upstream and downstream. This is upstream and downstream. If we want to be able to convert between these two, then we can do it by the loss terms here, which are related to these thermodynamic quantities, if you like. And these three equations are the ones that allow us to link them together. And I think the best visual way for us to think about this is in terms of Bernoulli, really, in this being written between the upstream part, which is these elevation head, pressure head, velocity head, and the pump that's put in as you go from upstream to downstream. So these are the three parts that are in the upstream part. And as we go downstream, this has to be a horizontal line in terms of energy space and includes elevation downstream, pressure head downstream, velocity downstream, and the losses that are occurred in going from upstream to downstream. And so this is perhaps the best visual way of thinking about it. We've only done it, we could do it for a general case for Reynolds transport theorem, but we've chosen not to do that because we'll only use it in this one-dimensional way. And again, this is a positive scalar value of mass flow rate. All right? We won't have much time, but there's some examples. So we've defined all the terms quite carefully. These are these linking parameters that allow us to be able to move between these two different relationships. I guess we've defined this one and this one. This comes straight out of our conservation of angular momentum behavior. So a lot of the work that we want to do in engines is being able to convert circular motion into something else. So a generator uses circular motion to generate electricity with an armature, and so there's a torque that's applied in this. So the amount of energy that we have within this, this is just denoting the fact that this is W dot. This is This is shaft, what we've called shaft work. Could be in or out, I guess, but we've called it in. So this is in power, units of power, which are joules per second, which are the same as watts. Right? And so this shaft work is due to the torque on the shaft, a force times a lever arm, actually, and multiplied by a rotational velocity. And so it allows us, if we know how much torque we're applying, how quickly the shaft is spinning, to be able to say how much energy we're either putting in or getting out of that system. Okay. So those are important. So that's, I guess, the third relationship that links these two one-dimensional behaviors. Okay. So, example. We have time to maybe very quickly do two examples. So, steam enters a turbine with a velocity of 30 meters a second going in, and come with an enthalpy that we know, and comes out of the turbine at 60 meters per second with a different enthalpy. So we know the behavior upstream, an inflowing velocity and an enthalpy, and an outgoing velocity and an enthalpy. And we want to find out the work output that we get from the system. If you look at equation 1, it should look a bit similar to what we've talked about. Equation 1 is the one we've talked about here. It has this equation here. Written in whatever way it's written. And again, it is written between upstream and downstream with a control volume. So this is really just a streamline that's going through the system from point 1 to point 2. Always use that convention. And this is the expression. This is mass flow rate. This is enthalpy, upstream, downstream, velocity, upstream, downstream, elevation, upstream, downstream. It's adiabatic, so there's no net thermal energy into the system. And there is shaft work either being put in or taken out of the system. So what we can do is we can divide this whole thing by m dot, the mass flow rate. So this makes this term 1, and this makes this work per unit mass flow rate. And if we do that, and we look at the terms, same elevation, so Z1 is equal to Z2. So we lose this term. We know that the upstream velocities and the downstream velocities are different. We know that the upstream enthalpies and the downstream enthalpies are different, and we can put those numbers in. So we have all of these numbers that we need, and we can put them into the system, which are, this is upstream enthalpy, downstream enthalpy, upstream velocity, downstream velocity. And if you look at these multiplying terms, they're just units of 1 to change the units. A joule is a Newton meter, so a joule divided by a Newton meter is just 1. A joule divided by a kilojoule, 1,000 joules is a kilojoule, and this is 1 kilogram. 1 kilogram meter per second squared is equal to a Newton. And so 1 kilogram meter per second squared is exactly the same as a Newton, so this is just equal to 1 as well. And this is the 2, which is here. And if you go through this, you end up with a certain amount of work coming out, which is positive, and that in this particular case, since the net work is out, that means energy is being put into the system to run it rather than being taken out of it. So this is positive, so it's net work into the system. Okay. So that's the one example for looking at this chemical response. The other one is just an exposition of Bernoulli. And so Bernoulli, if you remember, is looking at the losses in this system. If you write Bernoulli as we usually write it, as this, pump head in the system, the downstream part are pressures, it's just this. So I always tend to write it in terms of lengths because that's what I remember it in. But if you multiply this, for instance, by G, each of these terms by G, which is exactly what this is, then you end up with GZ, which is this term here. And instead of being V squared over 2G, you lose this G here. Instead of this being pressure divided by rho G, you lose the G here, etc. And these are just defined as losses in the system. So it's instead of being written in terms of a length, in this particular case, multiplying it by G gives you these losses directly in terms of work per unit mass flow rate, I guess is what it comes out as. And you just look at being able to put the right values in. So in here, you're looking at flowing from upstream to downstream. I'm not sure what the first one is. Yeah. So this is upstream, and this is downstream. And so we know what the conditions are here. What's the pressure? Atmospheric pressure, so P is 0. Atmospheric pressure, P is 0. Big reservoir, velocity 0. Big reservoir, velocity 0. So we can get rid of the pressure, get rid of the velocity terms, and we're left only with the potential energy terms, ZB upstream, upstream and downstream, the amount of work we get out of the system, and also losses within the system. And so if we rearrange in terms of equation 2, we've thrown away the pressure and the velocity terms, we can look at the shaft work which is done in the system, and so the amount of power we get out of the system is due to the potential energy that we run through the system minus the losses that occur as we run through these pipes, which has to be finite if it's a viscous system. And all this example is showing is that it's very important to write this equation in terms of upstream and downstream. If you look at the pump storage scheme where you alternatively flow it up here instead of down, then this now has to be the upstream and this has to be the downstream. And so the second part here is for flowing uphill. And the example basically shows that whether you're running flow from uphill to downhill, you get losses due to frictional drag. Also, when you're pumping it up from downhill to uphill, you have exactly the same frictional losses working against you. So you use energy in the system either way you do it. When I pull this bag across the table to me, I use energy to get it to the second location. When I push it back to its original location, I use energy again. And this is just an exposition of that. Flows downstream, you use up energy, dissipates as heat. You push it upstream to get to the same position with that potential energy then sitting up at the top reservoir. You've used energy again, dissipated as heat to get up there. So that's it. So have a look at what we've done. I realize I think it's a bit complicated. I don't know whether I explained it as well as I could, but basically it's Bernoulli's equation with a viscous loss term, and you only have to think it that way and use the conventions that we talked about. Okay? Thanks very much.